Thank you. And I want to also thank Luke Morrison, who has a great relationship with his senator. And Montana is one of those few states that has more senators than Congress people, I think. I encourage you to develop similar good relationships with your elected officials. So I'd like to turn it over now to Sebastian. Here we go. Engelman from IBM. He's going to be leading a panel discussion, and he's got a big panel, so I'm not going to take any more time, but invite Sebastian up here to host a live quantum marketplace. This is a program that we've been doing for several years now with a lot of leadership from Mark Whippich and Jasmine Cho, and we don't usually do them live, so we're excited today to have a live quantum marketplace on cryogenics for quantum. So over to you.
Yeah. Thank you for the introduction. So I'll just briefly outline here what we talk about, give a little bit of overview. Of course, I want to introduce the speakers, and then one of the main things is the roundtable live discussion. I think all the speakers have a brief that we want to be more than twice as efficient as at APS by giving really short speeches on what they want to tell us. And just the quantum marketplace is a place where we're trying to raise awareness of what is out there in the quantum field, to raise awareness and to facilitate collaboration, deals, and partnerships. There's generally sort of like two sides that you can find information. The one is on the Quantum Consortium page. They're listed by the affiliations, and then each of the affiliation has their little promotional videos for that. And the outward facing is also on YouTube, the channel for the marketplace. You can see all the recordings that have been produced with the help of QED-C. I would also draw special attention to the recently released update on the cryogenics programs that QED-C has been funding. There's been 4 programs that have come to a conclusion, and they have the reports out on the website. All right, a little bit about the trends and the things coming up. As Celia mentioned, I'm Sebastian Engelman from IBM. I'm also the vice chair of the Emerging Technologies TAC. And one of the key things that we want to accomplish for this year on the Emerging Tech is to have a recap and a refresh on the cryogenics roadmap. So there was an initial report that QED-C produced in 2019. It's 5 years later, so it's a good time to look at this again, look at what has worked, what hasn't worked, and where we need to go. So if you have ideas, needs, or wants, feel free to reach out to me or Saeed, the chair, and we'll be happy to try to incorporate it. So I'll update when we have more information on that workshop. I talked about the marketplace. There's lots of good information. I encourage everyone to look into that. And then also I would like to highlight the quantum technology roadmap, again, was produced with help of QED-C and NIST. I find it a great resource to sort of like understand where we are, where we need to go. And we want to use that to sort of like assess where we are. Generally speaking, cryogenics in the recent years have always gotten bigger. There's been new designs that have been introduced. Generally speaking, a lot of the improvements also have focused on convenience of the use. The goal was always this push button operation. You push it, you walk away. In some cases, you can even push the button in America, and it turns a cryostat on in the other part of the world, for example, Japan. A lot of the trends you've seen usually for the computation side of things have focused on how much qubits can you fit into the cryogenics. That gotten a lot harder question to answer because there's also been lots of improvements on the I/O interfaces. So you will see in trends that like initially everything started with SMA-based cabling that's been made a lot more compact, and now we start to see the introduction of flexible circuits as the I/O material of choice for cryogenics. The term invisible cryogenics, I think, was coined at the initial workshop. So I think that's one that I think you'll see very much incorporated in products that you can get these days. One of the things that was also mentioned in the initial workshop was the need for compact small cryocoolers. Again, you'll see here in the panel some of the developments that have been made in that regard. And the other thing that was also pointed out is continuous operation, no fail rate. Again, pay attention to the panel. I think you'll be able to see some great progress there. The other point I would like to mention is as cryogenics starts to become a lot more like a demonstrated capability, it still is a question. So if you go outside of the realm of talking to people that are invested in quantum and you talk to people that don't know quantum at all, a lot of times you still have to explain what cryogenics is. And I would again highlight, like in the year of quantum that we have, that probably is something that still needs a little bit of work. So onto our lineup. Like I said, we have a pretty packed agenda and a wide variety of field. So I will, I guess, try to go a little bit quicker here. But so first we have, here's Charlie Danaher from Danaher Cryogenics. We have Scott Jano, CTO from Lakeshore. We have Aaron Miller from Quantum Opus. We have Nick Rich from Northrop Grumman. Phoenix isn't here, but we do have David Gunnarsson, and we also have Corbin. I think I went out of order there. Okay, so I would, I guess, start with Charlie and then go from there.
Thanks, Sebastian. I want to thank QED-C for the invitation to be here. It's an honor to participate in this session. And before I get started, tell you about our line of cryostats, I just want to make a point that we are not quantum scientists. Rather, we like to consider ourselves like the Levi Strauss of this business, where we're just helping people do the job and make their life more efficient. So with that as a preface, I'd like to say that we offer several families of cryostats, the first being light and dilution refrigerators. Second is adiabatic demagnetization, or ADR cryostats. And third, cryostats with chase absorption coolers built inside. So a little bit more about our chase inside cryostats. We basically start with the world-renowned Simon Chase coolers, and we build full cryogenic systems around them. So they are fully incorporated, fully instrumented, fully automated. We offer these in several different chassis sizes for different experimental sizes. We offer these devices in either single shot or continuous 1K, single shot or continuous 300 milli-K. And what's really exciting is our charger model, self-contained dilution refrigerator cryostat without the usual hassles associated with dilution refrigerators like external gas handling systems and risk of loss of helium-3 gas and such. Turning to our ADR cryostat product line, ADRs offer a very elegant way to generate 100 millikelvin or 50 millikelvin cooling. Again, we offer these cryostats in different chassis sizes, fully instrumented, fully populated with wiring if need be. I want to bring special attention to our Model 107, which is a helium-3 backed single-stage ADR which offers very elegant 25 milli-K cooling, a great alternative to dilution refrigerators. And turning to Leiden Cryogenics, we represent Leiden Cryogenics in North America. Leiden has 30 years of great reputation of delivering wonderful, high-quality, huge DRs with base temperatures less than 8 millikelvin, a wide range of cooling powers starting at 250 microwatts, clear up to 2.5 milliwatts. Mixing chamber plate diameters from half a meter up to clear up to 1 meter. Two really elegant features of Leiden systems are, first, they're very convenient, hands-free lift system, which it's barely an exaggeration to say that a user can take apart and put back together a system with barely lifting a finger. The second one is a cold swappable probe, which allows the user to change a sample and experiment without warming up or disassembling the system. Lastly, I want to talk to you about our advances in rapid cool-down technology. We're working on two different fronts. The first is an invention to the pulse tube cooler, which greatly increases the cool-down power and efficiency of pulse tubes. The second one is our direct technology, which is a invention which distributes the cooling throughout the cryostat. So it's one thing to have a pulse tube that generates a lot of cooling. It's a whole other thing to distribute that throughout the cryostat to generate the cooling. This yields faster experimental throughput, faster results. This technology can be incorporated with liquid nitrogen or it's dry, and we're seeking patent protection on that. And we're really excited and can't wait till that this new technology is implemented in commercial machines and products and allows the users to get on with their life and experiments. I'll leave you with this contact information and look forward to the question and answer period.
All right. Well, thanks, Charlie, for getting us warmed up. Hello, my name is Scott Yano. I'm the CTO at Lakeshore Cryogenics. And today I'd like to tell you how Lakeshore is enabling quantum technology development. So first of all, who we are. At Lakeshore, our mission, we're really passionate about advancing science and technology. We were founded in 1968. We now have 3 locations for manufacturing and operations, 2 in Ohio and 1 in the Boston area. We've got over 40 international sales reps throughout the world in over 100 countries. We're an ISO 9000 manufacturer. But I think the coolest part about Lakeshore is we are routinely voted a top workplace by our employees. In fact, in Ohio, I think we're 10 years in a row, and we've hit it every year. So just a mention about our customers. Really our customers are several of you and some of the folks that you work with. But we got a couple areas. Space and defense and aerospace is a big part of our business. Big focus is national research and academic research at top universities throughout the world. And then finally, just about anyone making cryogenic equipment for scientific purposes are our customers. A lot of my fellow panelists up here. We might have some sensors involved in next generation ice cream flavors, but it's not really scientific, so we try to focus on these areas. And what do we do? So, Lakeshore is very well known for our temperature products, our calibrated cryogenic temperature sensors and instrumentation, as well as our magnetic sensors. But a lot of the world may not know about the work we do in materials characterization, cryostats, and especially our measurement software. So I'm going to spend most of my time talking about that today. But since we are Lakeshore, we got to start with thermometry. So Lakeshore, we're the world leaders in thermometry at Cryogenic Solutions, and there's been a ton of work over the years in kind of the millikelvin range, especially with all things quantum, right? And quantum and control of systems in that 10 millikelvin to 100 millikelvin range is hard. But some of my colleagues up here have really pushed the envelope and are going even colder in temperatures. South of 10 millikelvin, even south of 5 millikelvin. And things just get exponentially harder as we go colder. So at Lakeshore, we're trying to keep up with them and trying to improve especially our ultra-low temperature ROX thermometers down to colder and colder temperatures. As well as we're very glad that a lot of our customers want to put more sensors and more thermometers. So we're currently working to develop instruments that combine really great ULT performance, but also with more channels. And then finally, speed is important. We know a lot of times in these dilution refrigerators, you have to warm up the entire cryostat in order to do sample exchange. So we're trying to pack more power and more channels into our controllers to just allow that rapid warm up without having to deal with external amplifiers. All right, so that's thermometry. Now some other areas. Optical quantum architectures. It's really cool to see the trapped ion and the neutral atom folks really gaining some ground on the superconducting qubit technology. So we're supporting that work with our ultra-high vacuum cryostats. While these techniques don't, theoretically require cryogenics, in our business we like to say cryo makes everything better. So, an UHV cryostat really is a great test bed for development, and the cryostat in the middle there is a complete UHV system, and then the one beside it is actually intended to be inserted inside a larger system. So we work with our customers with various applications to meet their measurement needs. We've got a line of cryogenic probe stations, and believe me, if you need a large 300 millimeter semi-automatic system, some of my other colleagues up here can help you out with that. But at Lakeshore, we still specialize in smaller systems that prioritize speed, ultimate temperature, magnetic field capability, and we really try to work with our customers who are developing those quantum building blocks. So some examples up here, a great one is SNSPDs. We've got a lot of work characterizing going on. We know our customers want to go as cold as possible. We're doing our best, but combining probing and ultra cold temperatures is challenging. All right, so for quantum really to scale, we just need more cold measurements. All right, so a couple examples of how Lakeshore is enabling that. On the left there is what we call our infinite helium system. There are thousands of wet cryostats in the world right now that probably aren't being used because liquid helium is so scarce and so expensive. So we'd like to get those back online. So this is a product that combines the ease of use and push-button operation of a cryocooler with a legacy liquid flow system. So it's all automated, push the button, cool down, push the button, warm up, and it really does great to enable fast measurements. Another example is high cooling power. Now, the example shown here actually is a liquid system. Typically in cryogenics, we deal in microwatts and milliwatts. Well, now we're being pushed by some of our customers exploring cryo-CMOS to drive hundreds of milliwatts and even watts, okay? This is an example that we did. It's got 40 phase match gigahertz lines coming down in the cryostat to test multiple cryo-CMOS modules at the same time to really scale up production for this customer. And then I think the last example I have here is more complete measurement solutions. If any of you have ever made low-level electronic measurements in a cryogenic environment, ground loops can be really challenging. Getting the connections properly connected can be really difficult. So we're really working with our customers to try to help do that for them by not only supplying the cryogenic environment, but also measurement electronics so they can kind of get that speed to first measurement a lot faster. All right, that was a quick overview. I promised Jasmine I would keep it to time. So thank you for the opportunity to be here, and I look forward to the discussion.
Yeah, again, thank you for the opportunity to be here. My name is Aaron Miller, founder and president of Quantum Opus. We're in the Detroit area, kind of halfway between Ann Arbor and Detroit. It's a great place for manufacturing in particular, and really good resources at the University of Michigan. We were founded actually 13 years ago tomorrow, so we're just finishing up our first decade of business, and it's been an exciting ride. So I wanted to give a little bit of insight into our market. This has kind of been an interesting evolution over the last few years in particular. We start by having our research market was really our primary market, quantum researchers in the academics. So if you look at our business, about a little over a third of our business has been academic researchers. We also, then early on, half of our business was government research, half academic. But in the recent years, and so our, we have this nice established supply chain, I would say. We make our devices from silicon, the superconducting nanowire single photon detectors using the superconductors, all the way up into a packaged cryogenic instrument that's self-contained. And we have control over that entire process except the cryogenic portion of it. That's something we still purchase. But that's really nice for our government customers. They know that this is domestically produced here, and we have control over that at some level. What's been interesting is that our industry customers have grown to about a quarter of our business in the last few years, which is exciting because it means that the quantum ecosystem is actually grown enough that now we're an OEM supplier for other quantum companies, whether single photon detector, whether they have single photon sources or their photonic quantum computing systems. It's pretty exciting to see that growth in the recent years. So we supply mostly still to researchers and government academics, but we're seeing the growth in the industrial sector to the point where that may grow to be the dominant portion of our business in the next few years. So we offer single photon detectors. They're all the way from the small little chips that we make ourselves, nearly perfect performance. The S and SPDs are kind of the gold standard of photon detectors now, but we package them into compact and robust cryogenic systems. Desktop cryostats, rolling systems for the medical community, for researchers who want just 120 volts the wall, push a button, 3 hours later you're counting photons. It's all self-contained, internal pumps and everything. We also still work very closely with our research customers to try to expand our capabilities. Multiple devices, high efficiencies, high speeds, whatever it is, we're very adaptable. That's also a challenge because it means 80% of our systems are actually customized still. So that limits our ability to scale and grow. But it allows us to take ideas that people have and within a few weeks even test some of the fundamental ways to make changes and to adapt to their market. So that's pretty exciting. But one of the things that we really hope to do in the future is find those markets that are focused for high growth by having some sort of normal specification and hit those pretty well. So our customers, as I mentioned, started for the most part in the quantum industry. So we have quantum networking customers, fundamental quantum information science, and quantum computation. Those are the dominant customers that we've had, often in academics, or government research labs, but now kind of pushing into industry in all of these areas. Then we start to see also then these other companies who need good measurement tools for single photons because they have a product like single photon sources that need to be characterized very well. So they'll merge those two together so our tools are used in somewhat of an industrial capacity as just another $100,000 box you put on the shelf and it does what you want it to do. We realized pretty quickly in what we're doing, and my background at NIST, was that the ability to prove to ourselves and then to our customers that we understand the measurements we're making, that our measurements are reliable, required innovations in things like metrology. How do we know that we can trust the efficiency of our detectors to plus or minus 2%? Because you'll get a 98% efficient detector. What does that mean if you're within 2% of 100%? So we've got to be very careful. We can't have 6% errors on that and have confidence we know what we're doing. So we're developing kind of single photon metrological capabilities out of necessity, and I like seeing like Angela's talk recently about single photon metrology at APS, just really pushing even in the standards labs in Canada and NIST how to make these sort of calibration measurements for the quantum industry in particular. They have new demanding specifications. And in the quantum ecosystem, we're starting now to get to see that the future is, of course, in scaling to systems with hundreds to thousands of integrated detectors. So we have strong partnerships with waveguide and integrated photonics efforts at this point. What I will say too, which is kind of exciting, is that we have other peripheral markets. We aren't really a quantum sensing company. We are doing photon counting, so in that sense we're sensing something quantum, but it's fairly standard the way it's been done. It's been done for 50 years, we're just doing it better. But we see those applications then really help us as a business diversify our customer base in medical imaging, free space communication, places like this, which just helps everybody. If the market grows, the cryogenics get less expensive and more reliable, that's good for everybody. So we've really benefited from the partnerships that we've had in industry, in government, and in the industrial sectors, so that's exciting. Clearly, we need to know what's going on in the industry, so if you're an industry person, you're an academic, communicate with us. This is great. If we know what's coming down the pike in 1 or 2 years, we can probably have something ready by the time that market needs it. That's really exciting. But in particular, if you see a market that's going to scale, and the one that we see now is potentially quantum networking, that has a very well-defined specification for what the product is. Now we can start to make hundreds to thousands of units and those can be almost identical and on the shelf. So I'll probably talk a little bit about the supply chain part of it, but the idea is to make everything accessible, available to people, reliable, and de-risk essentially the photon detector supply chain. So there's contact information if you want to get a hold of us. Thanks.
Alrighty. Good afternoon, everyone. My name is Nick Rich. I'm a cryocooler research and development engineer with Northrop Grumman, and today I'll be giving you a brief overview of who we are, what we do, and what cryogenic solutions we have available to the quantum marketplace. So I'm here representing Northrop Grumman's cryocooler group. We're based out of Redondo Beach, California. And we are a cryocooler and cryogenic solution provider for sensitive, exquisite application spaces, such as quantum computing, applied superconductivity, deep space astrophysics, such as the James Webb Space Telescope, which we're very proud of, as well as an array of civil, international, and military United States government missions. And while we have traditionally been a legacy aerospace cooler provider, we are also available to the commercial marketplace as well. So focusing more on the quantum market specifically, as Aaron mentioned previously, we have seen a growing focus on deployable quantum-enabled devices. And in order to realize deployable quantum devices, effective thermal architecture and thermal packaging becomes really, really critical. And developing ruggedized, miniaturized, and productized versions of thermal packaging is one of the things we do really, really well. It's our bread and butter. So Northrop Grumman's cryocoolers, combined with our cryogenic architecture and packaging solutions, can help be the bridge between the technology that many of you are working to develop in the lab and bringing it out beyond the lab and into the field, into deployed devices. So our group, we are designers and manufacturers of Stirling cycle pulse tube cryocoolers and Joule-Thomson cryocoolers. And what really differentiates our coolers from a lot of other coolers in the market is that our coolers are designed explicitly for applications where performance, reliability, and stability are paramount. And as such, they have a very low exported vibration due to the compressor topology that we use. They're very highly power efficient, have a compact form factor, and low system level mass. We have cryocooler products that range from cold tip temperatures from 150 Kelvin all the way down to sub 4 Kelvin. We have distributed cooling capability through our Joule-Thomson cryocoolers. And lastly, perhaps most importantly for you all, our coolers are designed for 10 years of uninterrupted failure-free operation on orbit. And this translates to 0 life cycle maintenance cost and 0 downtime for your instruments or your devices. Just to really drive that point home, I've got our candlestick chart here that shows that for all of the missions that we have delivered cryocoolers for, we have a combined over 300 years of on-orbit operation without a single failure. And when you work with us, you're not just buying a cooler in a box. We do have options available for tailoring all of our cold heads and our cryocooler topologies to maximize performance at your specific operating temperature or condition, no matter what that is. And we also have decades of experience helping our customers develop not only end-to-end cryogenic solutions, but instrument and device level thermal packaging solutions, such as those we recently completed on DARPA's iSchool program or our DARPA's Near Junction Thermal Transport program. So no matter whether your device is embedded in one of the most complex space telescopes ever fielded, or it's embedded in a very small microchip array, Northrop Grumman's cryogenic solutions combined with our cryocoolers can help bring the technology and the devices that you all are developing, again, out of the lab on a benchtop and deployed into the field. So last thing I have for you here is a brief overview of the cryocooler products that we have available, with special emphasis on those capable of colder temperatures. So I don't know if you can see my cursor there, but beneath each one of the model names, we have the maximum input power on the left side, and we have the base cold temperature on the right. And just to illustrate that a little bit more clearly here, again, focusing on our hybrid pulse tube and Joule-Thomson coolers that are capable of providing heat lift at the much colder temperatures. We do have a wide range of TRL9 cryocooler solutions that are suited to quantum or quantum nascent applications, such as quantum computing, quantum photonic integrated circuits, both high and low temperature applied superconductivity, squid arrays, pre-cooling ADRs or dilution fridges, and as well as distributed cooling for quantum circuit arrays. So that's all the time I've got. Thank you for your time and attention. If you have any questions, thoughts, please don't hesitate to get in contact with us, either at our cryocooler inbox or my email there. Thank you all.
Hello, everybody. My name is Phoenix Dai, and I work on the technical business development team out in Boulder, Colorado for FormFactor. Today I'm going to talk a little bit about our cryogenic product portfolio and our role in the quantum ecosystem. So here you can see this is sort of a display of the main product portfolio of FormFactor at large. The boxed out area is where I work in the quantum cryogenics. And as you can see, this is a little bit of an overview of the company as a whole. We have over 2,000 people globally. We're a NASDAQ publicly traded company, annual revenue approaching 1 billion. And the quantum cryogenic team is kind of a relatively small sliver of the company. And these are some of the industrial recognitions that we have received recently. And we zoom into talking about our cryogenic test and measurement product portfolio for quantum industry. So here you can see our both our system level cryogenic products as well as component level cryogenic products. So on the left-hand side here is our millikelvin dilution fridge, and in the middle is our cryogenic probers, both at the chip scale for early stage R&D or low volume manufacturing purposes, and wafer scale probers that are more for people who are in industry scale up and high volume manufacturing. And the chip scale can go down to 2 Kelvin, as low as 2 Kelvin. 4 Kelvin is a standard. Wafer prober at the moment is at 4 Kelvin and can handle up to 300 millimeter wafers. And obviously we also have miscellaneous cryo test as a service. So we actually house an in-house wafer prober that you can come and pay to play type of setup to come try out our wafer prober for your test and measurement needs. And obviously we also sell component level cryogenically compatible probes, both electrical probe and photonic probes. And our role in quantum ecosystem at large is we do what we do at best, both at room temperature and cryogenic temperature. So we offer a cryogenic test and measurement to everybody who remotely needs anything cold or even at room temperature. And we will help you take your R&D in lab to all the way to full-scale production in high volume. And the application usually we see in the market for who would need cryogenic test and measurement are usually superconducting qubits or just devices that need superconductivity operating principles, or photonic devices, and obviously cryo CMOS and such. And if you have a need to contact us, here is one way to get hold of us, and we have the QR code that links to our website. And thank you for your attention.
Afternoon, everyone. My name is Corbin Tilleman-Dick. I'm the founder and CEO of Maybell Quantum, and it's awesome being here at March meeting. 4 years ago, we exited stealth at March meeting in 2022, and at that point, it was 7 of us with a vision for how cryogenics needed to change in order to better serve the quantum industry. And at this point, it's incredibly exciting to look across the industry and see how much has changed, see the progress that's been made by the industry, and feel like Maybell has hopefully been an important part of that. At this point, Maybell is over 50 employees based in Denver, Colorado, with systems in over a dozen countries right now. And if you look at our footprint, most of what we do is in Colorado. We've got 3 different manufacturing facilities in and around Denver that are where we build our systems, but we have a rapidly growing global footprint as well, with offices in Helsinki, Copenhagen, and Münster, Germany, in order to support our customers around the world. And when I think back to why Maybell exists, it candidly is because before Maybell, quantum was changing really rapidly. There was a huge amount of innovation going on in the industry, but dill fridges hadn't changed much for a couple of decades, and they really weren't ready for scale. And so back in 2022, Maybell launched what we called the fridge. And it's a 10 millikelvin dilution refrigerator with more wire capacity than any other fridge on the market at the time, that took up about 1/10 the space. It was 2 19-inch racks, roll them through a door, plug them in, turn them on, and it just worked. And we were really proud of that. We got that out into the world. We started shipping systems in 2023, and our customers loved it. They were happy with it, but we got some feedback that we'd given them all of this wire capacity, but they didn't have enough sample volume to really take advantage of that. They also wanted systems that were cheaper and could cool down faster. And so this year, we launched 2 new systems, what we call the Fridge Plus and the Fast Fridge. And the Fridge Plus takes everything that folks loved about the fridge, but it puts big doors on 3 sides to make access even easier. It gives you about 4 times as much sample volume, and it kind of pushes the envelope forward on usability. On the Fast Fridge, you have the option of either a 30 millikelvin base temperature for an industry-leading low cost, or you can have a 10 millikelvin base temperature, but on both of those, you get true overnight cool down. So if you leave the office, leave the lab at 6 p.m., turn the fridge on before you head out, by the time you're back in the next morning, your sample's going to be at 10 millikelvin, and you can do science, and you can warm up again before you leave the office that day. Finally, we have the Maybell Big Fridge. This one is to support customers who are pushing to increasing wire counts, increasing sample volumes, increasing qubit capacity. It's a remarkably powerful system and a remarkably capable system in terms of the number of wires you can put into it and the quality of the experiments you can do. Now, across all of our systems, we've driven uptime and reliability first and foremost, gotten rid of the most failure-prone parts of legacy systems. No scroll pump, essentially no rubber anywhere in the circulation line, 0 corrosive joints, so there's no acid flux, and 0 soft joints, no solder, no indium, no epoxy. All of those things are things that fail over time, so that when you buy a fridge today, maybe in a couple years it starts leaking. We've gotten rid of all of those. I like to say that unless you hit the dilution unit with a hammer, it's gonna stay leak tight forever. We've also done things to reduce mistakes, user error, things like getting rid of the liquid nitrogen dewar, getting rid of the need to take apart the system when you want to access your sample volume, Doors make sense. There's a reason that you don't have to disassemble your kitchen refrigerator to grab a Coke. You also don't have to disassemble your dill fridge now to touch your sample. We've driven some important improvements around the thermalization and attenuation layout, adding a 9 Kelvin plate that gives you cooling power in a stage where you really need it. We're talking even on our 500 microwatt system, more than 2 watts of cooling power below 9K. And our intermediate cold plate is able to run with about 8 times as much heat load on it as competitive systems while still keeping your base temperature at 10 millikelvin because of some important changes there. And finally, people sometimes ask, why is a fridge a square? It's not because we set about to build something different. It's because we set about to build the best possible interface for our customers. And this is a big driver of that. All of your wires load from the same direction. And that means even if you have hundreds or thousands of wires, you can load them on the insertion jig that comes with your fridge. And it's basically a table. You sit at the table, you do your work at the table, and then you stand the wires up like you can see in this picture, and you roll them straight into the fridge. You never have a postdoc holding 1 million wires in a wire tree, and you're never in the fridge trying to do these really fine manipulations that are better done sitting at a desk. It makes a huge difference for how you work with the systems. Finally, our software is based on open source libraries with Python APIs that allow you to integrate with it, use it, take the data from it, and run your system and your data the way you want to. And all of that is paired with industry-leading flex lines that are true coaxial cables at a density that's unmatched by any other coax in the industry. So that's what Maybell's built. That's how we're trying to contribute to this industry. Incredibly excited about this opportunity to share what we're doing and eager to answer questions as they arise. Thanks so much.
So, hello everyone, my name is David Gunnarsson. I'm CTO for Bluefors, one of the legacy companies in this business. So, I will give you a who, what, and why Bluefors exists. And we are now actually a 16-year-old company, founded in Helsinki, but now we have operation and manufacturing both in Finland and in US with sort of operation up in Syracuse. We are a little bit over 600 professionals from 50 nationalities, and we have an install base of more than 1,400 systems around the world. And I think that gives sort of a legacy of reliability, quality, and usability of the systems. So it's a strong history. So when 16 years ago, Bluefors came to be, there was sort of a paradigm shift when it came to how you use cryogenics, especially at the millikelvin temperatures. And I think that's the cryogenic revolution that sort of fed into different technologies, and quantum technology is one strong one that has sort of benefited from that. We have now, together with the Cryomeg and Bluefors sort of brands, a strong sort of product range, ranging from millikelvins all the way up to 80 Kelvin. So we are a full-scale cryogenic company in that sense. And we are getting more. So we will also, we announced a few months ago that we also now will start manufacturing dilution refrigerators in the US. So we are sort of broadening our manufacturing base to sort of minimize risks and sort of create a closer touch to customers, especially. What we do, we have heard earlier here, we are creating ultra-low temperatures, but we also add the addition of being a measurement system. So for different technologies, we don't only cool down your samples, we also make sure that the samples also can be interacted with. You can control them, and you can sort of read out what they are doing. Our customer base has originally been academic, but we do now, when different technologies getting closer and closer to industrialization, we do support both scientists and industries in getting cryogenics in a form. I think someone said invisible cryogenics, but it's just creating the environment that makes the technology shine. So I think that's our purpose. We, from the beginning, actually offered a scalable solution, especially for dilution refrigerators. Compared to how it was before, there was not the thought of how do you actually produce these things in a very scalable manner. And what we have been doing the last couple of years is developing our industrial supply chain. We are trying to make ourselves ready for the sort of big bang, to be sure that we can supply the volumes that is needed when the need comes. So our systems is used in many different areas. General research is, of course, a very strong base. That's where the foundation of all technology happens. But we are also present in MRI, NMR, MEG, and photon therapy, so we already have sort of an established ecosystem for cryogenics. Quantum, of course, is a very strong focus, and the reason I showed all the others here is that what we do in quantum, it also enhances cryogenics in general. So any technology that would shine with cryogenics now actually have a footprint to stand on. Then there's high energy physics and astro and cosmology. So I will just finalize my talk. So cryogenics for everyone, I think that is what we are about. We are a full stack cryogenics company, large range of products for different temperatures, and present in many different industries. And the last part, we do also have a very strong service network built up around the world, and I think that's also something that part of the industrialization becoming more and more important, to really have a total customer care. I didn't show so much about my products, but you can go to our webpage, bluefors.com, and read more about that. Thank you.
All right, now we come to the fun part. We'll have a little bit of a roundtable discussion. If there's any questions in the room, also welcome people to just stand up, go to the microphone, and then we can take those questions as well. So just to get a little bit of a discussion going here, we talked about cryogenics have undergone significant changes, and I'd like ask the speakers to just sort of like looking for your company, what is the innovations in the recent years that you're most proud of? And I guess we can just start maybe with Charlie.
Sure. Thanks. Is this mic work?
Yeah.
Okay. I guess what I would say to answer that question would be ease of use, and specifically advances in the software control system. So you don't have to be a cryogenic engineer and computer scientist to recruit on your cryostat.
Good. Scott.
Great. I'll piggyback on that and say, in addition to that, it's the measurements. It's, at the end of the day, our customers need to make very accurate, very precise electrical measurements inside these cryogenic systems. So it's really about, allowing, again, not cryogenic PhD experts to be able to make those measurements. Is really what Lakeshore is pushing towards.
I think from my point of view, I agree with the previous ones that it has sort of changed the use space. There's different users now. They need less cryogenic knowledge. So I think the systems and their use cases is sort of adding more value today. So you don't have to do a lot of work. So one of the things that we're very proud of is how the measurement infrastructure has sort of gone from being a very cumbersome thing 20 years ago to put in to actually be very modular. Bluefors were the first one to drive in sort of side loading, et cetera, to make sort of the accessibility to the system much easier. And now I think that's something that is important, like how you use the cryogenics.
I would say, to echo on to all the sentiments of the speakers before me, in terms of, I would say there are two trends I see that are sort of where the market is going in terms of innovation. One is people are way more interested in wafer level test and measurement, which was not really like on people's mind a few years ago. And another thing is people are way more interested in having some kind of very specialized function onto their cryogenic platforms. So these are two sort of specific trends that I think people are getting really innovative about in the market.
So
I guess it shouldn't be that innovative to put a door on something that's already called a refrigerator, but I'm proud of that one. But actually, even more than that, what I'm most proud about is the things that ensure that when you cool down the system, it stays cold. So I realize that feels trivial, and I think the first big step on that was driven by Bluefors. Full credit to Bluefors. Their systems changed the game, but I think Maybell has taken that to an entirely different level, doing things like getting rid of every soft joint in the system, no indium, no epoxy, no solder, doing things like getting rid of all of the acid flux, doing things like getting rid of the scroll pump and replacing it with a roots blower. There are a lot of changes that we've made that make it so that our customers can depend on our systems to not get in the way of the science they're trying to do. And I think more than putting a door on it, more than painting it black, which has become very popular in the industry recently, I'm really proud of the things we've done around uptime and reliability.
Very good.
All right. On the aerospace cooler side of the house, innovations that we're quite proud of, we've had several topological optimizations for a couple of our different cryocoolers, our pulse tubes and our Joule-Thomsons. The pulse tube specifically, we actually, through a research program sponsored by QED-C, developed approaches and techniques that enable us to field a purely pulse tube cycle 4 Kelvin cooler, which for high-frequency pulse tubes is a big accomplishment. And then on the Joule-Thomson coolers that we've had several adjustments to our topology that increase the total heat lift capacity at 4 Kelvin and below 4 Kelvin.
So Quantum Opus is extremely application-driven. So since we were single photon, we've been black since 2013. We didn't want reflected light, so anyway, we didn't start the trend. That's okay. But really proud, this is a silly thing, but really proud that our new systems can be run by real doctors. We have them in hospitals. They push a button. They roll it out literally out of a crate, plug it in a wall, push a button, and they're counting photons from brain scattering light measurements in 3 hours, and it's exciting. We're trying to, with the Bluefors product, we can get it down to 70 minutes, which is pretty amazing. So from warm to counting photons in less than 90 minutes.
Excellent. Great questions. All right, then let's switch a little bit, focus on the on your customer side, and I guess we'll start like this way from the other side. So Scott, what are your trends that you notice in your customers, and also if you could tell your customers what should they do differently?
Yeah, I'll focus on the industrial customers because that's our newest set that are the most challenging for us. We have to change what we do for industrial customers because academics or government researchers are happy with a quote and then getting a grant, and then 18 months later they get delivery of a system. Our industrial customers, even our first one, said, can we have this thing in 2 weeks? And so that presents a different set of challenges for us. So plan ahead would be a nice one for us, give us some time. But we're trying to accommodate that in the supply chain, and we can do that a bit elastically by buffering the cryogenic components. But it's a challenge, but it's something that's kind of exciting to deal with, is to try to be a reliable supplier within 2 weeks of a cryogenic system from the time you say go is kind of unheard of.
So kind of expanding on that, industry trends that we have noticed, even in our traditional market space, is the growing demand for actual deployable devices. So now that the technology is moving out of the basic research realm and more into devices that can actually be built and fielded. And in terms of what we would request that our customer base does differently, kind of on the nose, but focus on higher temperatures. High temperature superconductivity would be really, really great.
Don't do that.
Because ultimately, right, no matter how you slice it, these millikelvin temperatures, and especially as you try to scale up, they're incredibly power hungry and power intensive, no matter how you slice it. So.
Yeah, so I think we're seeing a bifurcation in customers. You have one class who wants smaller, faster, cheaper, and that is the priority. They want it cold in a couple hours, They want it as low cost as possible, and they want it delivered as quickly as possible. And then you have the folks who are pushing for high qubit counts. And for them, it's about scalability and reliability, making sure that the systems just work, that they're bulletproof to the highest degree that they can be, that you can plug a system in, walk away for many years, and come back and it's still chugging away at 6, 7, 8 millikelvin. We are pushing hard on both of those. And in terms of what I want my customers to do more of, buy more fridges. We have learned so much from our customers over the last little while, and the feedback we've gotten from them has led to better products already. Continuing to give us that feedback is the most valuable thing, but yeah, I would like as many fridges sold as possible.
Probably because the product that we sell are geared towards people who want to do tests and measurements and probing on their cryogenic operating devices. So I would say I have noticed a sort of a collective mindset shift, both in academia, researcher type, as well as industrial customers. So there's a mindset shift towards how do I make my devices more manufacturable? And how do I make my devices, how do I take my prototype devices to a commercializable product? So I would say there is a collective mindset shift to go from, I'm just interested in learning the physics of this, to how do I make this useful, and how do I make this a thing I can reliably manufacture to become a product that I can sell. So the questions in the customer's mind have shifted from, I'm studying this, to how do I use what I have studied to become something useful and I can profit off of it.
I think we had a lot of good points. I think this bifurcation that Corbin mentioned is a clear sign. I think half of business is academic, half is sort of more industrial, large-scale, different sort of way of approaching things. One thing that I think we see from new customers is that they need predictability, but it's not only technical predictability. You also need a total customer care. You need to have the service networks so that you actually have this intimacy and actually can react as soon as something is needed in the application where they are used. And I think that's something that is very important when you start building up this industrial supply chain. And in the end, that sort of just guarantees the technical predictability. I think someone said earlier, forecasting is very good, maybe because there's so many different needs and different asks from customers, and the earlier, the faster we can deliver. So it's sort of something that is always a challenge in this business, that waiting very long and then need it in a few months is very challenging.
I'll just quickly comment. I think I'm going to say the same thing Phoenix said, but yeah, to get to that those manufacturable products, the metrology needs to be there. It's not just can we get it to work, it's how well does it work, and how well does it work repeatably and reliably. So that's what we're seeing.
One trend that I would mention would be, hasn't been mentioned yet, is small, compact, low energy draw, even mobile. So something could be deployed to a bank, to a port of entry, but small, low energy draw mobile devices.
Great. All right, I think we have some live questions here. So the panel doesn't know what's going on.
So my question is, it's been about 6 months since Department of Commerce, BIS, put in place export controls that touch at least 3 of the 7 companies, maybe the rest of them. I'm kind of curious if at all that's mattered to you so far, and in what ways, or if you have any comment?
It's stressed out our customers a lot. They have to go through extra steps in order to get their systems. It's been okay. We've been able to manage through it, but it's certainly caused an extra level of concern from buyers, saying, are we going to be able to get it? And we kind of have to hold their hands through the process, get them there. It's a little bit of extra administrative work internally for Maybell. Not little, it's meaningful extra administrative work internally for Maybell, but more than that, I think it's stressed our customers out.
Thanks. I don't think everybody has to answer. If somebody else wants to add to that, but
I'm sure you do.
Kinda
Maybe
similar.
it's more the asymmetry. So of course, the control is needed to some extent, but then if it's still a free market for the rest of the world, it's a problem. So you need that base to sort of grow.
right.
Also.
Well, and there was this innovation in export controls where there was a sort of, if the country that you're doing business with has similar controls, then they're sort of inside the fence, and there's some free trade there. We'll see. I think there's always going to be some sort of pain as these roll out, but hopefully you're going to be able to educate your customers and things will work. There also was a reporting requirement with regard to deemed export and your non-U.S. citizens from certain countries. Did everybody have to do a report? Is that sort of working okay also?
So far, we think we're compliant.
Okay. QED-C is maybe here to help. My question actually is sort of related, and that is...
We're doing our darndest.
One of the impacts of export controls by the U.S. and others is it incentivizes innovation and development of indigenous capabilities in the countries where it is making impact, and that would include China, for instance. So I'm curious if what you're seeing, it's very hard to know what's going on in China. We're all sort of curious, and I'm wondering if any of you are seeing more development, R&D, competition coming out of that part of the world.
Yeah, just say significantly, definitely. The export controls are absolutely driving more innovation in those other countries. And just to comment back to, in addition to the products being regulated, it's also the end-use customers. You know, those lists are growing in terms of who we can't sell. And to the point earlier, it's creating a lot of uncertainty because, you know, we may have an order and then 3 months later, we can't ship to that customer. So it's driving a lot of uncertainty in the economy.
All right, I'm a laser guy that's going to ask a cryo question, so get ready. But before I do, I have to ask the Quantum Opus guy a photonics question. Your detectors, what's the recovery time from seeing one photon to the next?
What do you need?
But I mean, can you get nanoseconds? Like how?
Yeah, the fastest are about 6 nanoseconds.
About 6 nanoseconds. Wow, that's.
And but we're moving to try to make that about 10 to 100 times faster. So
Yeah. Oh, very cool. All right, the crowd question. The dill fridges, getting down to millikelvin, they still seem really big swap C to me. And so Danaher mentioned it, like getting the swap C down. You know, presumably there are laws of physics and sort of what sort of temperature gradients you have to have. And I mean, what are the realistic possibilities for making, you know, a small dill fridge, and what does that even mean? And so, you know, what do you guys see in, you know, 10 years' time? Like, is it laws of physics and they're just not going to get much smaller? Or I'm just curious your thoughts on this.
There's room to get a lot smaller, but yeah. So we see room to get, with no new physics, down to a quarter the size.
There
of a
are no
Maybell
new
fridge.
physics. Physics is physics.
Once you push much past that, you run into viscous heating issues that make it really hard to get too much smaller with a dill fridge, from our perspective. Others may have bright ideas, but that's kind of what we see.
So how small do you think you might
Quarter
get?
rack.
Okay.
And as far as the efficiency goes, there's some talk about employing magnetic cooling instead of using a pulse tube to go clear down to 3 or 4K, to use a pulse tube and stop at a higher temperature, because pulse tubes are very inefficient going on down to 3K.
Yeah.
So there's other advances to be had there.
All right.
I think size is also like how much do you need to cool?
Yeah, what's the
This is-
thermal mass that you got to get down?
Be- Because if they're gas driven, there is a volume dependence. So
Right.
I think, yeah.
All right, thanks.
How do your customers train their employees, or how do you train your employees' customers? Or do some of your employees' customers already know how to use your systems from previous education? And do you think there needs to be an expansion of education on how to use your systems?
I can start on the photon side. It was actually kind of new to us when we got into this and we're selling our first few systems. It was actually amazingly valuable for us to go and visit and train, because it saw the application firsthand, get a scientist there to see what they're doing. We started to realize we were offering a product that actually wasn't optimized for what they wanted. So that we started then much more deep technical discussions very early in the sales process, and that has helped us a lot. The training is extremely valuable because there are things that we take for granted working in, say, fiber optics. When someone's free space optics and they've never used fiber, there's some things that just change, so you have to think differently about it. And in the cryogenics end too, things that are obvious to us that you have to wait a little while before you open a cryostat after you turn off the switch. There are things like this that seem obvious to someone who's worked in the field, that if you have a good training base and a good relationship, what we found is that when our customer feels comfortable to reach out and they're not embarrassed to ask dumb questions, they make fewer dumb mistakes. So a good relationship there has been extremely valuable. Yep.
Very good.
I think this, as we said earlier, we have very different customers and they change their behavior. So more traditional customer maybe had more knowledge and know more what they were buying, while new ones were not. But from a company perspective, when it comes to cryogenics and when you start growing a supply chain, you need to sort of interact with other people other than physicists. There is a gap, and I think the education that is needed is maybe more in mechanical engineering should design for cryogenics. Electrical engineering should design for cryogenics. And I think if you look at schools, it doesn't exist in curriculums. They usually have a quite narrow sort of space for temperature, but in cryogenics that goes to 10 millikelvin, you have 5 orders of magnitude of challenges. So I think that's something that is very important to start that journey.
Yeah, and I think the challenge is from both directions, right? We absolutely need more folks trained on cryogenics. We also need to make cryogenics much easier to use so that a technician with limited training can come in and succeed deploying quantum systems. Until we can do both of those things, increase the workforce of trained individuals and make the systems really easy to use, we're going to have a big gap. And we're certainly working on that actively at Maybell.
So I have a quick follow-on to what I thought you were going to say, which is we need to make systems that can be used in educational settings. How many of you offer something that is at a price point that your kind of typical university, maybe not even an R01, but an education, a physics department, you know, in a liberal arts college can afford to have one for their students to use?
I think the new fast fridge is at that point. We have non-R1 universities excited about it.
Very good. I think we're like a little bit over, so let's go, I think, to the last one, maybe with one-word answer. So we're asking if there's challenges that you think need sort of like a common perspective, what do you think would you highlight? And again, let's just try to keep it short with it.
Scalability.
Not keeping up with the developments, not keeping pace.
I think the knowledge base that we just talked about, I think, is a very important aspect for the scaling. Yeah.
So I'm trained as an AMO experimental physicist. So I actually, I don't know if how many of you guys know that there's when laser was first invented in 1960s, which is more than 60 years ago, it was a solution without a problem. We didn't know how to use it. We didn't know what was useful for. Obviously, this is completely not the case today. It's almost ubiquitous where laser is being applied. But what I am kind of seeing right now is I see a lot of cryogenic-related customer applications, but what their devices are being used for, I am kind of getting that sense we might get into a laser problem where they have a device, they haven't found what their devices are best used for. And we are obviously on the supply chain to these customers. So I think if they feel pain, at some point we're going to feel pain. So that's kind of what I'm seeing.
I'll do scalability in China.
Extending on scalability, whenever you scale up, again, just highlighting the extraordinary power draw that's going to have to come for these systems in order to scale them.
On the other side, we're trying to make as portable as possible, so that part of the QED-C Cryogenics grant was to try to push these things down to sub 300 watts, sub 100 watts, total wall draw for something and get to sub 3 Kelvin. That would revolutionize what we do for scaling, because now you get deployable, reliable, handheld cryogenic systems for photon detectors. That would be useful for networking. The challenge for all of that, of course, there's the cryogenics part, but we also need an application that has well-defined specifications. If we have to customize all of our systems, we can't scale. So if we can know this is the bullet, the silver bullet for a scalable system, then we can hit that. We just don't have that yet. There's not consensus.
All right, so thank you all for this great roundtable, and let's thank the speaker again.